Quantum mechanics has a reputation problem. Say the word quantum, and most people picture the same things. A superhero shrinking down into a glowing, swirling dimension fighting purple warlords from another timeline. Particles existing in two places at once. A cat in a box that is somehow both alive and dead until someone checks. It all sounds like science fiction. The kind of thing that lives inside of a movie screen or on a chalkboard in a lecture hall, far, far away from your actual everyday life. But that reputation couldn't be further from the truth. Although the quantum world might seem to us like it's far out of reach, its effects permeate through everyday life. It's in everything, from how a plant can pull energy out of sunlight with almost no energy loss at all, something no solar panel ever built by humans has managed to do. It's the reason a doctor can see inside your body without making a single incision. And it may also be one of the reasons why, right now, your own cells are quietly accumulating damage that decades later shows up as aging and sometimes cancer. This is not a story about the future of technology, although be patient, we will get to that. It's a story about right now, about what is happening inside of you and all around you, at a level of reality so small that it breaks human intuition. This is how quantum mechanics affects you every day. I'm sure you don't need me to tell you that quantum physics is hard to understand. Even scientists who work with it daily are saying things like, "Don't try to visualize this," and "the math works even though nothing about it makes sense." And while that is true for abstract quantum theories, the consequences of quantum mechanics itself aren't hard to see. You're surrounded by them. In fact, I will bet you $1 that you are holding one or looking at one right now. Your phone, your tablet, your computer, pretty much every piece of modern tech with a chip in it works because of quantum mechanics. The transistors inside processors, somewhere between 10 and 15 billion of them in a modern chip, exploit a quantum property called electron tunneling, where an electron passes through a barrier that it couldn't under the classical understanding of physics. So, to better understand it, picture a ball rolling towards a hill. If the ball doesn't have enough energy to get over the top, it simply rolls back down every single time. That's the world that we live in, the world of cause and effect. Nothing gets across a barrier it doesn't have the energy required to climb. Now, replace that hill with an energy barrier, and replace the ball with an electron. In the quantum world, an electron isn't a solid, hard little ball with one fixed location. It behaves more like a wave of probability smeared out across space. And that wave-like nature has a very strange consequence. There's a real, measurable chance the electron simply turns up on the other side of the barrier without ever having had the energy needed to climb it. It didn't jump over the hill. It didn't find a crack in the hill to slip through. As far as physics is concerned, it was never anywhere in between. One moment, it's on one side of the wall, and the next, it's on the other. That is what is called electron tunneling, and it's the literal mechanism that your phone's processor depends on. Engineers build the chip's billions of transistors around precisely tuned barriers, and they rely on that real, calculable probability of tunneling to switch each transistor on and off billions of times per second, encoding the information that becomes your texts, your photos, your search results, everything. If you were to take tunneling away, the device in your hand simply wouldn't exist. And it's not just about a processor. The screen you're looking at right now produces light through quantum mechanics as well. Electrons drop between energy levels and release photons that shine as light. The GPS signal that your phone uses to navigate relies on atomic clocks whose precision depends entirely on quantum energy transitions. The camera sensor works through the photoelectric effect, the discovery that won Einstein his Nobel Prize in 1921. Classical physics expects that shining a brighter light on a piece of metal should knock electrons loose with more energy, the same way a bigger wave hits a swimmer harder. Instead, brightness did nothing to the electron's energy. Only the color of the light mattered. A dim violet light could knock electrons free instantly, while a blindingly bright red light couldn't knock a single one loose, no matter how long you left it on. The only explanation was that light itself wasn't a continuous wave delivering energy smoothly. It was arriving in discrete packets, photons, each carrying a fixed amount of energy determined by its color, and an electron only gets ejected if a single photon hits it with enough energy in one shot. Every time you take a photo, millions of photons strike the silicon inside of your camera sensor and knock loose a specific matching number of electrons, and your phone simply counts those electrons, pixel by pixel, to build the image that you see. It's all pure quantum mechanics. The best part about this is that none of this is controversial. These are textbook applications. They are, in a strange way, the boring quantum story, the one where the quantum weirdness gets tamed into stable, measurable engineering. The interesting quantum story is different, though, and it begins with an experiment on green sulfur bacteria published in the journal Nature in 2007. There's one terrifying way quantum mechanics could affect you personally in the not-too-distant future. Quantum computers could eventually break much of the encryption that protects the internet today. That means information that seems secure right now could one day become exposed. And bad actors are already preparing for that through something called Harvest Now, Decrypt Later. They collect encrypted data today and hold on to it, betting that future quantum computers will be powerful enough to unlock it. That data can include everything from financial information and crypto wallets to personal details like your name, your location, employment history, email address, phone number, and more. Once that information is exposed, it can be used to target you in ways that are hard to predict and even harder to undo. That's why I reached out to Incogni to sponsor today's episode. Incogni helps remove your personal information from places you may not even know are storing it. Data brokers, people search sites, and online directories that treat your identity like a product. By law, many of these companies have to delete your data if you ask. But doing it yourself can take weeks, months, or even longer. Incogni handles the process for you by automatically and continuously sending removal requests, then following up to help keep your information out of reach. And with their new custom removals feature, if you find a site exposing your personal information, you can send the link to Incogni, and their team will work to get it taken down, even if it's outside of their usual network. To protect yourself, go to incogni.com/Aperture deal and use the code Aperture deal to get 60% off an annual plan, because they can't harm you if they can't find you. Now back to our story. A team of researchers at Lawrence Berkeley National Laboratory were studying photosynthesis. Not for the first time. Photosynthesis has been studied for well over a century. What they were looking for was something classical physics has never really been able to explain. How do plants transfer solar energy with an efficiency approaching 100%? Well, here's the problem. When a photon of light hits a chlorophyll molecule inside of a plant, it creates a little packet of energy. That energy must travel through a complex arrangement of molecules to reach a reaction center, the part of the plant that converts solar energy into chemical energy that the organism can use. Now, classically, you would expect this to work like a ball rolling through a pinball machine. Energy hops from molecule to molecule, and each hop, a little bit of that energy is lost as heat. You would expect the process to be 50 or 60, maybe even 70% efficient at its best. Biological systems always lose energy, that is the rule. But photosynthesis doesn't lose energy, or it loses barely any energy. The transfer is near perfect. So when the Berkeley team looked at why, using a technique that could observe the quantum behavior of energy in real time, they found something that should not have been possible at room temperature in the warm, wet, chemically chaotic interior of a living cell. What they found was quantum coherence. The energy wasn't hopping randomly from molecule to molecule, it was spreading like a wave, simultaneously sampling every possible path, finding the most efficient route and collapsing onto it, all in less than a fraction of a nanosecond. This is what the 2007 spectroscopy data showed happening in a living bacteria, and what the 2010 follow-up demonstrated was even more remarkable. Quantum coherence had been observed at cryogenic temperatures before, but everyone assumed that the warm, wet, noisy interior of a biological cell would destroy it almost instantly. Decoherence, the process by which quantum superpositions collapse under environmental interference, was supposed to be the rule. But shockingly, coherence survived for at least 300 femtoseconds, which is extraordinarily long at biological scales. The energy in the FMO complex maintained its wave-like quantum character. It survived the thermal noise of the surrounding proteins. Researchers modeling the transport process found that a purely quantum system with no environmental interference would actually be less efficient. Some degree of dephasing, some degree of noise from the warm molecular environment created what they called environment-assisted quantum transport. The protein scaffold surrounding the chlorophyll molecules was not just a passive container. It was tuned across billions of years of evolution to maintain exactly the right level of quantum noise, to hold the system in the narrow band where coherence is preserved just long enough to do its job. Evolution didn't just discover quantum mechanics, it learned to use the environment as part of the quantum machinery. Now, consider what this means for energy technology. The best commercial silicon solar panels available today convert roughly 22% of incoming sunlight into electricity. Just 22. The best laboratory silicon cells reach around 29%. These are not failures of engineering. They are hard limits imposed by the physics of how classical materials interact with light. The energy that arrives in a photon must match the energy gap of the semiconductor, or it's just wasted. Photons above the gap waste their excess energy as heat. Photons below the gap pass straight through. The theoretical maximum for a single-junction silicon solar panel, what physicists call the Shockley-Queisser limit, sits just above 33%. Photosynthesis operates near 100%. And this isn't to put down the current solar panels that we have. They are marvels of technology in their own right, and photosynthesis is not perfect. It doesn't convert sunlight all the way to electrical current. It stops at chemical energy. And the overall biological systems that plants use to take energy from the sun has other much larger inefficiencies at later stages. So this isn't saying that photosynthesis is an evolutionary pinnacle and that solar panels are a technological failure. Instead, I'm just pointing out that the specific step that matters, the initial capture and transfer of photon energy to the reaction center, the quantum coherence step, the efficiency is essentially perfect. And if we can harness these lessons and implement them into solar panels, the results could literally change the world. And researchers have been doing just that. In 2025, a team at the University of Cambridge reported finding a quantum effect inside an organic semiconductor, a material once thought was far too warm and chemically complex to sustain any quantum behavior. That allowed light to be converted to electricity with what they described as incredible efficiency. Earlier work had achieved quantum yields exceeding 130%, meaning more energy carriers were produced from the process than there were incoming photons, by engineering systems that exploit a quantum phenomenon called singlet fission. These are early results, proof of concept experiments in controlled conditions, but they point towards a future where solar technology is redesigned, not around classical physics, but around the quantum strategies that plants have been using since the Proterozoic. If that technology matures, the implications scale so quickly. A solar collector in space, freed from the atmosphere and operating with quantum-level efficiency, would gather energy at a rate that changes what is possible for our entire civilization. But this is the horizon. There's more immediate territory that we can cover. Because quantum coherence in photosynthesis is only the beginning of what biology has been quietly doing with quantum mechanics. And the next example is considerably stranger. The question is no longer, how does life capture energy? It's, how does life know where it is at all? Consider a European robin in its first year of life, born just this past spring. It's October now. As the ground hardens and the insects it depends on disappear, the bird needs to leave before winter cuts off its food supply. It has never made this journey before, but it still knows exactly where to go, navigating thousands of kilometers across Europe through cities and coastlines and mountain ranges to the same wintering grounds its ancestors used. How? The obvious answers don't work. Visual landmarks help, but robins have been studied to navigate correctly in windowless rooms with no view of the world. Sure, stars help, but robins navigate equally well on overcast nights. Something else has to be doing it, something so sensitive that researchers spent decades refusing to believe it was real. The answers live inside the robin's eye. Specifically, inside a protein called cryptochrome embedded in the retina. When a particle of light, a photon, strikes the cryptochrome molecule in the bird's retina, it knocks loose an electron. That electron travels across a chain of molecules inside the protein. What is left behind is a hole, an absence. And together, the electron and the hole form what physicists call a radical pair. Two charged particles now separated in space, but still quantum mechanically linked. Their spins, the quantum mechanical property that makes them behave like tiny magnets, are entangled. Now, here's where things get far stranger. The Earth's magnetic field is extraordinarily weak. You can't feel it. A compass needle responds to it, but only because we've engineered the needle to be sensitive. A single molecule shouldn't be able to detect a field that faint. The thermal noise inside a warm biological cell should overwhelm it entirely, but the entangled radical pair is not responding to the magnetic field the way a compass needle does. It's responding through quantum mechanics. The field shifts the relative spin states of the two particles, changing the rate at which they interconvert between two quantum configurations, a singlet and a triplet. These configurations produce different chemical products. The brain reads the ratio of those products as directional information. The bird is not sensing north the way a compass does. It is reading the geometry of the magnetic field through the quantum state of entangled electrons in its own eye. It may literally see the magnetic field as a visual overlay on its perception of the world. The experimental evidence for this has accumulated steadily. Birds with cryptochrome knockout lose their magnetic orientation ability. The compass is light-dependent, requiring specific wavelengths to activate, exactly what the radical pair mechanism predicts. Disorientation patterns under artificial magnetic fields match the mathematics of quantum spin dynamics. And in December 2024, a paper published in Nature Communications added something new. Even tightly bound radical pairs, ones that physicists had previously assumed were too close together to be sensitive to a field as weak as the Earth's, can in fact respond to it, provided the recombination process is strongly asymmetric. The mechanism that enables this is called the quantum Zeno effect, a phenomenon where continuous quantum measurement effectively freezes a system in a coherent state long enough for it to interact with the field. The bird's cryptochrome may be exploiting, at the level of quantum measurement theory, a mechanism that physicists only formalized in the 20th century. What can I say? Evolution got there first. But magnetoreception is only one example. And in some ways, it is the most forgiving one to accept, because it involves a specific, isolated protein with a measurable function. The next example is more intimate. It touches something you do thousands of times a day without thinking: smell. The conventional explanation for how smell works is what scientists call the lock and key model. An odorant molecule floats into your nose, drifts towards the olfactory epithelium at the top of your nasal cavity, and then snugly fits into a receptor protein the way a key fits into a lock. The shape of the molecule determines the receptor that it binds to, and the receptor determines the signal that's then sent to your brain. Different shapes equal different smells. The model is elegant. It is also, at the edges, wrong. Here's the problem. Take a molecule called cyclopentadecanone, a large ring-shaped compound with a distinctive musky smell. Now, replace every hydrogen atom in that molecule with deuterium, a heavier form of hydrogen with an extra neutron. The shape of the molecule is identical, its mass is slightly different, its chemical behavior is the same. The lock and key model says that it should smell identical to the original. You can probably guess where this is going. It doesn't. And both humans and fruit flies can tell the difference. The physicist Luca Turin proposed an alternative. Your nose on this account is not a lock, it's a spectrometer. What the olfactory receptor actually detects is the vibrational frequency of the molecule, the quantum mechanical oscillations of its chemical bonds. Each molecule has a unique vibrational signature, and the receptor reads the signature through a process called inelastic electron tunneling. An electron crosses from one part of the receptor to another, only when the energy it releases exactly matches the vibrational mode of the odorant that's docked between them. The strongest piece of evidence for this came from an experiment with fruit flies. Flies, trained to avoid deuterated acetophenone, when offered a choice between a nitrile compound and its non-nitrile equivalent, avoided the nitrile. Deuterium and nitrile have different shapes, different chemistry, and different almost everything, except for one thing. Their vibrational frequency is nearly identical. So the flies weren't responding to the shape of the molecule, but its vibration. Now, I should say ahead of time, this does remain contested. Receptor-level studies have struggled to replicate the isotope effect under tightly controlled conditions, so the debate is genuinely open. But the fact that it is open is itself significant. Decades after the lock and key model became canonized in our textbooks, the mechanism of the most personal and ancient sense that we possess is still not resolved. We don't actually know how smell works. And the deepest quantum story in the body may not be navigation or smell at all. It may actually be in the enzymes. Every chemical reaction in your body is catalyzed by an enzyme. Digestion, respiration, DNA replication, neurotransmitter synthesis, the entire operating system of biological life runs on enzymes. So thank you, enzymes. And since 1989, when researchers first measured what is called the kinetic isotope effect in the enzyme alcohol dehydrogenase, the evidence has been building that many enzymes do not operate through classical chemistry alone. So the test is simple in principle. Replace the hydrogen atom being transferred in an enzyme reaction with, again, deuterium. Deuterium is chemically identical to hydrogen but twice as heavy. Classically, it should behave the same way in the reaction. But quantum tunneling depends critically on mass. If you were to double the mass of the particle that's doing the tunneling, the probability of tunneling drops sharply. So, if swapping to deuterium slows the reaction down more than classical chemistry predicts, then tunneling is involved. The reaction slows down in enzyme after enzyme. Proton tunneling is not a curiosity in biological chemistry. It is a part of the mechanism. The reason your body can run the reactions that it needs to run at body temperature at the speed life requires is partially because protons inside enzymes do not climb over energy barriers. They just pass right through them. Your body is exploiting a quantum mechanism to metabolize food, to breathe, to think. All of these, the coherence in photosynthesis, the entanglement in the bird's eye, the quantum spectroscopy of smell, the tunneling in enzymes are cases where quantum mechanics helps, where it enables things that classical physics alone cannot achieve, where biology reached into the quantum world and pulled something useful back out. But those are the cases where it works. The disturbing part is what happens when quantum mechanics does the same thing, but instead of helping us, it harms us. Inside the nucleus of almost every cell in your body, roughly 2 meters of DNA is folded into a space smaller than the grain of sand. That DNA is held together by hydrogen bonds, chemical connections between the base pairs that form the rungs of the double helix. Adenine binds to thymine, guanine binds to cytosine. The pairing is specific, it's stable, and it is foundational. If the pairing fails during replication, the genetic code is copied incorrectly and mutations occur. The question that biologists assumed they had answered was, why do those pairings occasionally fail? The standard explanation was thermal fluctuation. At body temperature, molecules are constantly vibrating. Occasionally, that vibration gives a proton enough energy to jump to the wrong position inside of a base pair, temporarily changing its chemical behavior and causing a mispairing during replication. It's all classic physics. It's predictable, random in its occurrence, but comprehensible in its mechanism. In 1963, a Swedish physicist named Per-Olof Lodin proposed something that the field largely set aside for decades. He suggested that the proton doesn't jump over the energy barrier, it's tunneling through it. Now, this distinction matters enormously. A proton jumping over a barrier requires energy. It requires the thermal kick to be large enough. It is a relatively rare event, controlled by temperature, and the probability drops sharply as the barrier gets higher. A proton tunneling through a barrier doesn't require that energy. It passes through the barrier regardless, because in quantum mechanics, a proton is not a hard sphere, but a wave function with a non-zero probability of existing on either side of any barrier, regardless of whether it has the classical energy to get there. Tunneling in this context produces what is called a tautomeric form of the base pair. The proton ends up in the wrong position. The base pair looks almost identical to its normal configuration, but behaves differently during replication. The copying machinery reads the altered base, pairs it with the wrong partner, and then the mutation is written into the new strand. So for a long time, this was considered theoretically plausible, but probably too rare to matter. The tautomeric forms were thought to be so short-lived that they would almost always revert before the replication occurred. Then researchers at the University of Surrey ran the numbers properly. Using an open quantum systems approach, modeling the full quantum dynamics of the guanine-cytosine-hydrogen bond, including the influence of the warm, noisy cellular environment, they found two things. First, quantum tunneling contributes to the proton transfer rate at a level several orders of magnitude larger than classical over-the-barrier hopping. Second, the probability that a given base pair is in its tautomeric form at any moment is roughly 1 in 6,000. Now, that sounds small until you consider that your genome contains approximately 3 billion base pairs. Run the calculation, and you realize that the number of tautomers present in your DNA at any given moment is somewhere in the hundreds of thousands. So most revert harmlessly before replication, but the ones that do not, they're copied, and the copied mutations accumulate. That's aging, that's cancer, that's genetic disease. These are not purely classically driven events. They are, at the very least, in part, quantum mechanical events. The errors building up in your genome across a lifetime are partly the consequence of protons passing through barriers that they shouldn't be able to cross. The quantum world is not just enabling life, in the same motion it is eroding it. And this opens into something that is harder to sit with than any of the previous examples. There is a tendency to treat quantum mechanics as a scientific topic, something contained within physics departments and biology laboratories, something that matters for technology in the abstract, for research programs with long timelines, and for discoveries that will arrive comfortably in the future. But the real disturbance of quantum mechanics is not what it does to science, it's what it does to the human experience. You are not a classical object operating in a classical world. The decision that your cells make, the errors that your genome accumulates, the energy your body extracts from food, the information your nose sends to your brain, the way a bird knows which direction is south, none of these processes are classical at the deepest level. The boundary between the quantum world and your world does not exist the way you think it does. It's not at the edge of a physics laboratory. It runs through the middle of your biology. This matters in the abstract philosophically, but it's also starting to matter in ways that are specific, immediate, and civilizational in scale. Quantum mechanics is reshaping the infrastructure of the modern world, and the timeline on that change has recently compressed sharply. Almost everything that you do online is protected by mathematics. When you send a message, or make a payment, or log into an account, access a medical record, the security of that action depends on the fact that certain mathematical problems are computationally difficult. Factoring a very large number into its prime components, for instance, is something a classical computer cannot do in any reasonable time frame for numbers large enough to be used in modern encryption. RSA encryption, which secures a significant portion of internet traffic, is built on this hardness. So is the elliptic curve cryptography, which protects cryptocurrency and digital signatures. Quantum computers do not attack these problems the same way classical computers do. A quantum algorithm called Shor's algorithm can factor large numbers exponentially faster than any classical approach. When a sufficiently powerful quantum computer exists, RSA and elliptic curve cryptography will be broken. For a long time, the consensus among security researchers was that this threat was real, but distant. The quantum computers needed would require tens of millions of error-corrected qubits, a generation away at least. Well, the consensus has shifted. In 2025, a Google researcher named Craig Gidney published revised estimates showing that breaking RSA 2048 encryption might require fewer than 1 million physical qubits, roughly 20 times fewer than previous projections. In early 2026, a Google white paper on elliptic curve cryptography reduced the estimated requirement further still, suggesting the cryptography protecting most digital signatures and cryptocurrency could be vulnerable with fewer than 500,000 physical qubits. IBM's current systems operate at over 1,000 qubits. The gap between where quantum hardware is now and where it needs to be to break modern encryption has narrowed faster than almost anyone predicted. And sophisticated actors are not waiting. The strategy now has a name. Harvest now, decrypt later. Adversaries collect encrypted data today. store it, and wait for the quantum hardware that will let them read it. Information that must remain confidential into the 2030s is at risk today. And this isn't theoretical, this is operational. And all of this, every quantum computer being built, every encrypted file being harvested, every post-quantum standard being drafted, traces back to the same physical reality as the chlorophyll molecule, the radical pair in the robin's eye, the proton passing through the hydrogen bond in your DNA. The physics is the same. It's just the scales that change. The consequences in every direction are arriving faster than we expected. The question is no longer whether the quantum world affects your life. It is whether you understand it well enough to navigate what comes next. There is a temptation, when faced with all of this, to feel that the quantum world is encroaching, that it's arriving from physics textbooks and particle accelerators into territory that it doesn't belong, that the reliable, the solid, the cause and effect world that you have always inhabited is being quietly dismantled from beneath. But that framing is flawed. The quantum world is not steadily approaching us. It has always been there. So what's new isn't the physics of it all. What's new is our awareness of it. The classical world, the world of solid objects and predictable forces and clear cause and effect, is not the foundation of reality. It is the surface. It's what quantum mechanics looks like from a distance, once you average over enough particles and enough time for the underlying uncertainty to blur into something that appears stable and predictable. A table feels solid because quantum mechanics, operating at the scale of atoms, produces an effective repulsion where matter is compressed. The sun rises predictably because of quantum tunneling, operating at the scale of protons, produces a fusion rate so well regulated it has not varied meaningfully in billions of years. You didn't leave the quantum world when you walked out of your physics class. You never lived anywhere else. The familiar world, the one your senses navigate and your intuitions trust, is a high-level description of a quantum reality. It's accurate the way a map is accurate. It's useful, navigable, but it's not the real territory. The territory is this: particles that exist in superposition until measured, energy that spreads as a wave through every possible path simultaneously, protons that pass through walls, electrons whose spin states remain linked across space, a sun that shines because of an event so improbable it happens to any individual proton roughly once every 10 billion years and yet occurs billions of times per second across the stellar core. This is the ground you're standing on, but it should be embraced, not feared. If quantum coherence is the reason photosynthesis achieves near perfect energy transfer, then the question for solar technology is not how to improve on silicon. It's how to replicate what a blade of grass does. Researchers are already asking this question seriously. The 2025 Cambridge findings, the 130% quantum yield results, the quantum dot solar cell advances, these are the early indications that the quantum strategies biology has been running for billions of years are translatable into engineering. Scale that translation to its logical conclusion. A solar collector engineered around quantum coherence, freed from the atmosphere, and orbiting the sun at close range, part of a Dyson swarm, would gather energy approaching the efficiency of life itself. The physics of a leaf applied at stellar scale. The total energy output of the sun, harvestable by a civilization that understood the quantum world well enough to build the tools. The quantum body points in another direction at the same time. If proton tunneling in DNA is a significant driver of the mutations that accumulate into cancer and age-related disease, then the next frontier of medicine is not purely chemical, it's quantum mechanical. The target isn't the tumor, but the tunneling event that preceded it, perhaps decades earlier, in a single base pair in a single cell. Drugs designed to stabilize hydrogen bond geometry in genomic regions to reduce the probability of tunneling at sensitive sites would represent a fundamentally different approach to the oldest enemies of biological life. These are not science fiction timelines. They are the natural extensions of experiments that are already published in peer-reviewed journals in the last few years. Quantum mechanics does not make the world stranger than we thought. It reveals that the world was always this strange, and that what we called ordinary was always just a description of quantum reality at the scale where our senses are happening to operate. The robin navigating by entanglement is not an exotic exception to biological life. It is an unusually visible example of what biological life has always been doing. The chlorophyll molecule running a quantum algorithm is not a curiosity from a 2007 paper. It's a window into the mechanism that has kept almost every living thing on Earth alive since photosynthesis evolved 2.5 billion years ago. And perhaps the strangest thing of all is this. A universe governed by physics so counterintuitive, so fundamentally resistant to classical logic, so deeply committed to uncertainty and superposition and tunneling and entanglement, somehow produced, in the 4 billion years since the first self-replicating molecule, a creature capable of noticing just how strange it all is. This is why, according to Einstein and Spinoza, you are no different from the universe, just different expressions of the same quantum entity. Click the video showing on your screen right now to learn more about that.